Okay, now for the second part of the fundamental theorem of calculus. Now before I jump into this, I just want to make a note to you that if we're doing an antiderivative of f of x dx, and its antiderivative is f of x plus c. But does it really matter what variable we're using? As long as u du match, this would be f of u plus c. If it was the integral of f of t dt, then it would be the antiderivative f of t plus c. That should not bother us that we are changing our variable there. Because I think the one thing that confuses students the most about the second part of the theorem is this idea that all of a sudden I'm going from x's to t's here. Well, there's a reason why I'm changing the variable inside the integrand, and it has to do with the fact that I am going to be using the variable x as one of my bounds. And since I am using x as one of my bounds, I can't also use x as the variable in the integration because I've used it. You can't use it to mean two different things. And so since I am very specifically putting x in that location, then I can't use x in the integrand and in the differential part. So we just conveniently choose another letter to use. So that is the only reason that we're doing f of t dt, because I have already used x in that location. Now, the second part, what we're basically doing, so instead of me finding the net change from A to B, notice now I'm finding the net change between A and X. I'm not actually going to be finding a number like I was doing before with the definite integrals. Because I am making the upper bound of my integration a variable, I will end up with a function of x, because it will depend on what this x is. What you want to think of this is going to be an accumulation function. It is going to give us how much has accumulated between a and x, the accumulation function between a and x. And so it's going to end up giving me a formula. All right. Now, for example, if the function f of t, the derivative that we're looking at, happens to be positive, then we can also define this function as the area function, but only if we know that it's positive for the entire time from a to x. But let's take a look at what happens here, and let's see why we're doing this. Okay, first off, let's prove that we have a function. So little f of t dt is going to be the graph that I'm giving you. So I'm giving you the rate curve, right? So this f of t is giving us the rate. This is your derivative that I'm giving you, right? And because it's inside of here, then we know that when we're doing accumulation, that we're going to work our way to the antiderivative. All right, so let's look at what this does. See, this is capital F. This makes a difference. So capital F of 2 says I want to find the definite integral from 2 to 2 of f of t dt. I want to know how much has accumulated from 2 if I don't go anywhere. Well, hopefully you can answer that question and say that it is 0. All right. So a point on the function, the antiderivative capital F, is going to be 2, 0. All right, if I do capital F of 9, then I'm going to go 2 to 9 f of t dt. All right, and then so now I need to do this. We recognize that we can calculate definite integrals using area. Okay, and if I can calculate it using area, I'm going to figure out my accumulation. I'm going from 2, let's just change color here so we can see what we've got. I'm going from 2 all the way up to 9. So I'm essentially calculating this area right here, which hopefully you will notice has 2 parallel sides, so it's a trapezoid. So I average the bases from 2 to 7 is a base of 5. from 2 to 9 is a base of 7, so I average the bases and I multiply times the height, which is 20. So we end up with our 12 over 2, 6 times 20, or 120 for that one. So 120 is how much area we have accumulated from 2 to 9. If I take a look at f of 15, capital F of 15, now they're asking me to calculate from 2 to 15 of f of t dt. So I'm taking the area I just calculated, and I am definite integral, so now I'm losing in the next section. I'm going to 15, which is right here. So now I need to lose from the 120 that I was currently at. I'm going to lose this area. So the area of this portion down here, my bases, so we're going from 9 to 15, so we have a base of 6. I'm going from 10 to 14, a base of 4, so I average my bases, I multiply times my height, so my area is going to be 50 here. So I take the 120 that I already accumulated, and I lose that 50, so now I'm at 70 for my accumulation. And then we want f of 18. Okay. So f of 18, I'm now going from 2 all the way to 18. What's the accumulation from 2 to 18? From 2 all the way to 18. So now, the nice thing is you don't have to keep recalculating. I just go, well, I take where I was, and I add this additional area in. Again, I have a trapezoid. The bottom base going from 15 to 18 is 3. So we'll come up here, area equals 3. Plus the other base goes from 16 to 18, so 2. Divide that by 2, multiply that by the height, which is 10. So we end up with 5 times 5, or an additional 25. So I take where I was at 70 and I add my additional 25 in, which would put me at 95. All right, and then f of 0. So now remember, we're going, the accumulation, we've defined this to be from 2 to x, so 2 to 0 of f of t dt. From 2 to 0, now remember, you're going backwards through the interval, so we know that that is, because it's above, it's going to be a negative number. So I'm going to calculate this area, because it's a triangle. So this area would equal 1/2 my base times my height, which is going to give me 20. And because I went backwards through an interval that was positive, it's going to be losing it back, taking it away at that point, and so we would be at negative 20. So the idea of defining this function, what you have to basically recognize, what I have just calculated is essentially several points on this function. This accumulation function f of x contains, if I were to graph it, the points 2, 0, 9, 120, 15, 70, 18, 95, and 0, negative 20. So I'm actually creating, by plugging in values of x and calculating the accumulation of area from the position x equal to 2, that I can create this function. Okay? Now, let's take a look at this problem. We're going to use the first fundamental theorem of calculus to find a simplified expanded version of this f of x. And then once we find it, we're going to find its derivative, because I want you to notice something here. So f of x is defined to be, now this problem we're going to go 3 to x of t squared plus t plus 1 dt. So what we're going to do is we're going to start out the process by recognizing we're calculating net change or accumulation. So I need to find the antiderivative. So t squared plus t plus 1 is the derivative of a known derivative that we can work backwards from. T squared would be the derivative of, whoops, let me change back to a color here, would be the derivative of t cubed 1/3, plus the t, its antiderivative would be t squared 1/2 plus t. But because we're calculating net change, we're evaluating this from 3 to x. And now you see what we're doing here. This is my kind of antiderivative. This is kind of like your f of t, that you found the antiderivative, but it's a function of t. But now I am going to calculate the net change by plugging in the end bound and the beginning bound. So I'm basically going to now calculate this f of x minus f of 3. Now, and this is kind of, maybe I shouldn't call, the bad thing about this is that what I don't like is that our notation kind of falls apart. I don't like, since I already used f over here, let's use g just because I want to, so they're not the same. So this g of t, if I take the derivative of g, I get my f of t that we had inside of here. Okay? So we plug these values in. So I get 1/3 x cubed plus 1/2 x squared plus x minus, right? Then you're going to plug in 3. And so we put in our 1/3 times 3 cubed, which is going to be 27 over 3 or 9. And then we have put in our 3 here, 3 squared, we're going to have plus 9/2, and then plus 3. So we're going to end up with, as a final accumulation function, of 1/3 x cubed plus 1/2 x squared plus x, and then this ends up being what, 12 plus 4.5, 16.5, so plus 16.5. Now, so this is this function that we have, but do you notice something about that? They now want you, now that we found it, to take the derivative to find f prime of x, which means we're taking the derivative of, with respect to x, of this expression that we started with, right? But instead of taking the derivative of this, if you want, we'll put parentheses around that, I can basically take the derivative of what we found the net change or the accumulation to be. 1/3 x cubed plus 1/2 x squared plus x plus 16.5. What is the derivative of this? Hopefully you'll recognize that's x squared plus x plus 1. Now, do we notice anything about this? The definite integral process of finding this net change finds an antiderivative over here. Then it plugged in x and 3. Now, the key here is to recognize that when you plugged in 3 over here, what did we get after we did that portion of it? We got a constant. So you end up essentially with the antiderivative of this with an x instead of a t here, plus a constant. So if I go to take the derivative of it, this portion right here, the derivative of an antiderivative is exactly back to where we started from. The only difference is now it's a function of x, not a function of t anymore, that we've managed to get into the x by doing the substitution up here. So the interesting thing about this fundamental theorem of calculus part 2 says that if we define this function, this accumulation function, by going a to x, that this starting value is kind of going to set a constant. And so what we will end up with will be an antiderivative plus c here, an antiderivative plus c after I do this calculation. So the accumulation function is going to basically be an antiderivative function plus a constant. The constant is going to be set by whatever this low bound is. But if I'm going to then take the derivative of this antiderivative plus c, I go right back to the integrand, the f that I had in here. The only difference is because in the process of going this way, this is now a function of x. So when I take the derivative, I end up as a derivative that is in terms of x, not in terms of t. And you might think, well, this is really a weird thing. They're telling me to take the antiderivative and then take the derivative. That's essentially what you're doing. That the starting value is irrelevant if they're asking you to find a specific antiderivative because you have a set beginning value. And then I say take the derivative. It's not going to make any difference to us. You're going to be able to go right back to what we started from. So if we take a look at this, we're going to be like, okay, I don't have to go through the process. We're recognizing a shortcut that if I want to take the derivative of this accumulation function, all I have to do is go, oh, it's going to equal secant of x, and I'm done. I can walk away. If I want to take the derivative of this, does it really matter what is in this location? Does it matter where I am starting from? Actually, no, it doesn't. Where I start from sets the constant. The derivative of a constant drops out. So it doesn't really matter what it looks like in here, and it actually doesn't matter that I'm using p in here. We don't care what variable is used in here. It's really just a placeholder. So this says we're going to find the accumulation function, which is going to end up being an antiderivative as a function of x plus a constant because of the 5, and then I take the derivative of it. And the derivative of an antiderivative will send me right back to the same function that was in there. The only difference, it will now be in terms of x. Okay. Same thing over here. Here's my function inside. K is my variable in the integration. But after I perform the definite integral, I'm going to end up with an accumulation function that is going to be an antiderivative as a function of x with a constant that is related to the pi where I started from. But then I want to take the derivative of that. So the derivative is simply going to be e to the x square root x plus x squared all over ln of x. It's kind of a weird rule, but if you think about what you actually did, you found an antiderivative with a constant that was set by a beginning value, and then you turned around and took the derivative of that. That it should make sense how we get back to this. Now, the second fundamental theorem of calculus, or the second part of this, we actually have a more general form. So the form that we're looking at here is the idea that we can plug in x and have a variable here. But notice that this bound, it might not just be x. It could be where your bounds are functions of x. So let's kind of think about what we're doing here. Now I'm just going to kind of put some notation in to see what's going to happen. Let's define, all right, that we have an antiderivative of little f here. I'm going to call it big F. All right? And that antiderivative that we find initially would be f as a function of t, but then we're going to evaluate that antiderivative that we found by plugging in your low bound and your upper bound. So what this is going to give us, okay, now is going to be, by the net change, fundamental theorem of calculus part 1, our antiderivative, we're going to plug in g of x, and then we're going to subtract plugging in h of x. All right, so that's just this portion inside of here. We calculate an antiderivative, we perform net change. But now what they're asking me to do is to take the derivative of this. So what they're actually asking you to do is to take the derivative with respect to x of an antiderivative that has a composition with a chain rule in it. So now if I want to take the derivative of an antiderivative, let's think about what happens. The derivative of the outside function, big F, is little f, that's right there, with a stuff inside, times derivative of the stuff. this is nothing more than chain rule. This is the derivative of f of g of x with respect to x, because the derivative of an antiderivative of stuff, this is my technical terms, with respect to x would equal little f of stuff times the derivative of the stuff with respect to x. That's what we're basically doing. And then I do the same thing over here. I take the derivative of the antiderivative, which gets me back to f of stuff, the derivative of this goes here, back with the stuff in it, times the derivative of the stuff. This is the most general rule, and it's nothing more than chain rule. All right, so let's see how this works. Let's look at the examples down here. So I first recognize that this isn't the easy one, because when I look here, I've got a constant here, so we're like, yay, but this is not just an x. This is a function of x. So as soon as I recognize I have that, I make a note to myself that I'm going to need to use chain rule. So to take the derivative, I first think about what the antiderivative is. Secant squared is a known derivative of what? Secant squared is a known derivative of tangent. And then we're going to take the derivative of tangent, and so I would get back to secant squared, but I'm not really taking the derivative of tangent. What I'm really taking the derivative of, and you're not going to need to write this step, I'm just trying to help you because we're at the beginning. I'm going to take the derivative of tangent of 2x cubed minus tangent of 1. So when I go to take this derivative, this is a constant, it's going to go away, and what I have left, derivative of tangent, is going to be secant squared. So we would get secant squared of the stuff inside times the derivative of the stuff, 3 times 2x squared. So we end up with a final answer of 6x squared secant squared 2x cubed. Now what we're trying to do in this process, okay, when we're doing this, is we are trying to shortcut having to write down all of these steps. That we want you to realize that I don't even really need to know the antiderivative. That this portion right here is not something I need to know in order to do this. I actually don't even need to know this in order to do that. All I'm doing is recognizing that I must have had the secant squared of the bound times the derivative of the bound, that I can just plug that in and get the derivative. So let's look at the next one, and we'll do that one. Now the difference in this one, though, is to realize that you plug the 7 in, the constant will happen in the antiderivative kind of at the beginning instead of the end. If we were to take this integral, we would get an antiderivative. I'm not even going to do it. I'm just going to call it f. We would plug in the 7, and then we would get the antiderivative, and we would plug in e to the x. So if I want to take the derivative with respect to x of this, then the derivative of the antiderivative would go back to here, but that's a constant, so it goes away, so we get 0, minus, this is the antiderivative with stuff inside, so the antiderivative, if I take its derivative, goes back to this, but it'll still have the stuff inside. But then I have to follow that with the derivative of the stuff, which is e to the x. So our final answer here is going to be minus e to the 2x minus 5e to the x times e to the x. And if you want to, you can distribute this through and simplify it, minus e to the 3x minus 5e to the 2x. So the idea is that we can use this idea of chain rule to do something that looks very complicated, but yet I'm essentially taking the derivative of the antiderivative. All right, let's do one more example of this, and then we'll stop this video. This has bounds that are functions, both here and here. So again, in my mind, what I'm thinking of is that I want to find the derivative of f of x. So I'm taking the derivative with respect to x of an integral, which is going from 2 plus sine of 2x to 3 to the x of ln of t dt. Now, I don't really care what the antiderivative is. I know what that means, so in my head what I'm thinking is that I have found an antiderivative. I don't even need to find it. I don't know what it is. I found an antiderivative. I plugged in my upper bound, and then I'm calculating net change, and I plugged in my lower bound. So even though I don't actually know what it is, or I don't even care to find it, I know that I am calculating net change and plugging in my bounds. Okay? And so now I want to take the derivative of it. So the derivative of the antiderivative goes back to what's in your integrand. So it would be natural log of r3 to the x. But then because there's a chain rule problem going on here, I would have to be like, oh, okay, I need the derivative of 3 to the x, which is 3 to the x times natural log of 3, minus the derivative of the antiderivative goes back to my integrand, so ln of 2 plus sine of 2x times my derivative of what's inside, which would be derivative of sine of 2x, derivative of sine cosine 2x times 2. So make sure you're multiplying this together. So that's just an idea of showing you, basically we're finding the accumulation function, which is related to the antiderivative, and then taking the derivative of antiderivatives. We have a little bit of chain rule involved.